Hello. How's everybody doing? Still people coming in. Again, real quick, move in. There's seats up front, guys, gals. Come on in. All right. You guys ready to hear all the things Kubernetes? Yes. Cool. All right. Yeah. All right. Well, please welcome two fine gentlemen from Google, Eric and Tim.
Thank you very much. It's great to be here today. My name is Tim Hawken. This is my esteemed colleague, Eric Toon. We're going to sort of hand off a little way through. We're going to sort of split this talk into two parts. So we have way more material than we do time, so I'm just going to bust right into it. So if we can move forward. Oh. Kubernetes. You guys have heard Kubernetes a few times today if you've been paying attention. Kubernetes is this thing that we built a couple years ago. Eric and I both worked on the Borg team, our internal container management system at Google. We started building this Kubernetes thing a couple years ago as a container management system. What is a container management system? You all know what containers are. We posit that once you start to run more than a few containers, you need some help managing them. And we thought that Kubernetes could bring some of the things we learned about how to do this through Borg to the rest of the world. So we built it as a container management system. But it turns out, man, I don't know why the clicker's not working. It turns out we built a platform instead of a product. It turns out there's a lot more things that people want to do with their containers than we could possibly have planned for, and a lot more environments that people want to use their containers than we could possibly ever support. So it's a subtle distinction. What makes a platform versus a system or a product? A platform is fundamentally something you have other people build on. Right? It's a thing that you stand on to build upwards from. And while we didn't intend Kubernetes to be that at the beginning, it turns out it's actually a pretty cool thing to do, and it's a pretty great fit for it. And people are doing things that we never could have imagined. Let's look a little bit at how people are using Kubernetes and what sort of extension points they wanted out of Kubernetes. We look at it and we split the space into two basic concepts. There's Kubernetes as an abstraction layer over your infrastructure. This is so you can run it in Google Cloud or in Azure or in Amazon and not really be concerned about the differences between those clouds. And for that sort of problem, you need this idea that we call infrastructure extensibility. You need to be able to make sure that all of your platforms sort of meet the same level so that you can stand on a level field across different environments and build up from there. There's this other side of Kubernetes as a framework for building distributed systems. To do that, you want API extensibility. You want the ability to take the system and make it do things that we never thought about. So you can maybe think of it as doing the things we planned for and doing the things we didn't plan for. Oh, it works. So these two API modes, they come with different goals. When we're talking about infrastructure extensibility, it's really about leveling the playing field. It's about portability. It's about making sure that the project can scale, right? It's about making sure that I don't have to take pull requests for all of your plugins, for all of your storage systems, for all of your networking things, and balloon the Kubernetes code base in a way that is really unmaintainable. And it's about autonomy. It's about giving you, the end users, and about you, the vendors and the distributors, the freedom to build a product that you want to build without having to run through me. On the API extensibility, it's about customization. It's about taking some idea that you have that maybe nobody else has ever thought about and making it work and doing it again without running through me or through Eric or through the rest of the Kubernetes team to do this. This encourages new uses, new things to do with the platform. And it's about autonomy. It's about giving you the power to do the things that you want to do without having to deal with us. So Kubernetes is a big project. We've got something like 20,000 contributors across 100 repos, if you consider all of the people who contribute to the bugs and the docs and everything else. For the last 2 years, we have spent an incredible amount of time on the topic of extensibility, about building extensibility into the system, from all the way down to the infrastructure, which is the area where I tend to live, all the way up to our APIs. We have at least a dozen API extension points, and probably more, depending on how you define things. At the bottom there is a link that you can follow along. So I'm going to talk about infrastructure extensibility. So let's start with everybody's favorite piece of infrastructure, the network, right? There is no such thing as a common network. Every network is a snowflake. There are no two that are different, at least I haven't found them yet. And there's no way that you can build a one-size-fits-all solution for networking. So we looked at networking, we said we have to have some sort of plug-in, some extension point here that users can configure. So today, previously we had plugins that were built into the system. It was the sort of plugin where you send me a pull request. Not a great plugin model. So now we have this thing called the Container Network Interface, CNI, and it's a standardized interface that's used by a couple of different container orchestration systems like Mesos and Kubernetes. And it is a way for you to provide, as a vendor or as a third party, a custom network driver that sets up your containers and the networking for them the way you want them to be set up, whether that's IPv4, IPv6, or MAC VLAN, or bridge, or point-to-point, or VXLAN, or whatever. It's a pretty widely used project, and it underpins the default implementation in Kubernetes. There are lots of vendors out there who are already shipping customized versions of CNI so that you can, as a user of Kubernetes, download their plugin and install it and run it with your network. In the future, we're looking at possibly moving to a more imperative RPC-based model, very tightly coupled. I'll talk a little bit more about the RPC-based model in a couple minutes. We're also talking about maybe making some of the couplings between different plugin interfaces a little bit tighter so that we can extend the system better and more effectively. And we've got a bunch of proposals open. The network space is incredibly busy. There's people who have all sorts of ideas. So we've got lots of fun new proposals for ways to extend the system into multi-network and multi-IP and all sorts of crazy stuff. Again, things that we could never have thought about before, but that plugins and extension points enable. The other most common piece of infrastructure that people think about when they talk about container systems is storage. There are a lot of storage technologies out there, right? Everything from spinning disks to SSDs and everything in between, and clouds and everything else. And a lot of vendors came to us and said, we want to support Kubernetes, but I don't want to write a plugin for Kubernetes and a plugin for Docker and a plugin for Mesos and a plugin for Cloud Foundry. So we sort of end-of-lifed our older plugin models, which were something we called Flex. And we've got this new thing called CSI, the Container Storage Interface, which is, again, a standardized interface. We're working across Docker and Mesosphere and Cloud Foundry and Kubernetes to define a pretty rigorous specification for what it means to be a storage plugin. And what's cool now is all the storage vendors out there can write one plugin, they can test it against one test framework, and they can be reasonably confident that their plugin will work in different container systems. I think that's pretty cool. And I think it's really sort of the first time that all these parties have come together to collaborate like that. The end goal here is to take all those plugins. We've got about 25 in-tree plugins, and we're going to move all those out into CSI plugins, and then we will have maybe 5 in-tree plugins left at the end of the day. It'll be great. I love deleting code. It's the best part of the day. So we've also got these things called device plugins. So it turns out ML is kind of a thing. And people are really excited about doing ML, but in order to do ML, they need access to their accelerators, their GPUs, their TPUs, their other things. How do we plug those things into Kubernetes? Well, Kubernetes has a generalized resource model, but we didn't have a way to extend that resource model. So we've now got these device plugin API that is, again, an RPC-based API. It follows the same pattern as CSI. And it allows you as a vendor, as an individual, to write a plugin fairly simply that exposes your hardware into Kubernetes, and now you can schedule against GPUs. So if you have your favorite GPU device, you can expose it into your scheduler, and your scheduler knows how to take your workloads and schedule those containers on machines that have those GPUs, allocate the GPU to you, and make sure that nobody else steps on your toes while you're doing it. So this is pretty cutting edge. This is beta in our most recent version of Kubernetes. So pressing forward, we've got container runtimes. Anybody heard of a container runtime called Docker? So Kubernetes started off, and the word Docker was just sprinkled liberally throughout the code base. I mean, it was everywhere. There was hardly a file that didn't have the word Docker in it somewhere. And it made it really difficult when people came to us later and said, well, I want to do something that's different than Docker. I want to do Rocket. I want to do Hyper. I want to do clear containers. And so we spent an enormous amount of energy disentangling Docker code from the rest of Kubernetes and squeezing them all off into a little module that we now call the Container Runtime Interface. You guys might notice a pattern in naming here. And what it does is it simultaneously cleaned up the code while we were doing it, but it also enables people to, again, fairly trivially write their own runtime plugin and change the way Kubernetes works. Google announced fairly recently that we're supporting this thing called gvisor, which is a different approach to secure container execution, and it's leveraging the CRI to make it work. Docker has this thing called Containerd. Red Hat has this thing called Cryo. It's kind of amazing that people can do these really interesting things without talking to us. So there's a few lessons that we learned through the infrastructure parts here. I'm breezing through these, but a bunch of our plugins started as exec. Exec plugins are really easy to write and they're really easy to think about. It turns out that in practice, they're hard to deploy, they're hard to manage at scale. A lot of modern OSs are read-only file systems. You can't just copy a file into the file system and expect it to be executable. And so we see this evolution away from from exec plugins towards RPC plugins, highly coupled plugins. We also see an evolution from sort of loose specifications to tighter specifications, and this really neat trick of running your plugins as jobs in your scheduling system. So a lot of the CSI plugins and everything else, they run inside Kubernetes as containers, which is a pretty neat trick. So then we introduce this entirely other pattern called controllers. And controllers, you may have heard of them, you're at a container conference. Controllers is this idea that you watch the world and you watch what you're expected to have in the world and you try to reconcile these two things and bring them together. And controllers is really fundamentally the pattern that Kubernetes is built on. And in fact, if you look at the way Kubernetes is componentized, each of the components, except for the API server, is itself a controller or a set of controllers. Our scheduler is just a controller. Our node agent kubelet is just another controller, et cetera. What's cool about this pattern is it allows you to observe and extend the behavior of pretty much any resource in the system, whether those are resources that we've defined, like pods and services, or whether those are resources that you've defined, which is what Eric's going to talk about in just a minute. Another example of controllers is cloud providers. To drop Kubernetes onto Google Cloud, you need an entirely different set of control loops than you need to drop it onto Amazon or to drop it into your own data center. Cloud provider is a separate controller that watches the Kubernetes API, and with no secrets, no back channels, no back doors, it programs your cloud to react to Kubernetes. Another example is services, which is our network abstraction, virtual IPs, and load balancers. It's just a controller. There's no special magic there. If you don't like ours, you can throw it away and replace it with your own. So there's so much more that I would love to talk about. I'm already over my time. There's things like key management, there's things like load balancing and network policy and firewalls and DNS and schedulers. I could go on and on about it, but I'm going to hand off to Eric because I think it's actually way more interesting to go, now that we've built the platform, to go up from there.
Thanks, Tim.
Green is forward.
So I had a whole segue plan between mine and Tim's, and as I was sitting here waiting for my turn, I was staring at this AV equipment back here, and I realized it's a perfect analogy for the split we're talking about. On the front, you can't see it, but you can imagine it. It's like an old stereo. It's got a bunch of lighted buttons and knobs on the front, and it's pretty well thought out. That, to me, is the API. In the back, it's got a bunch of different plugs. You can plug in different standards like mic level and RCA and everything. That, to me, is the infrastructure extensibility. The infrastructure extensibility you set up one time, and you mostly kind of leave it. On the front, that's what you use day to day. Well, what Kubernetes does with extensibility of that API is it basically replaces that with a touch screen. And now you can add new buttons that you dream up later without rebuilding your AV equipment. Basically, there's two kinds of API extensibility we offer. One is the way to add new resources to your cluster. Resources are things like a service or a deployment. And then we add a way to add custom policy hooks, which I probably won't have enough time to talk about today. But the idea with a custom policy hook is you can intercept every change a user makes to either a custom or a built-in API, and then decide, do I want to allow this? Do I want to tweak it? Do I want to add a label to this resource before they create it? And how do you create extensibility? Well, you actually talk to a special API that is used to configure extensibility. So we're talking about APIs that add and or modify APIs. So this gets a little bit confusing even for me, and I work with it every day. So for me, I find it useful to try to ground it in something real. And since this is DockerCon, the thing I'm going to ground it in is Docker. So you guys probably know Kubernetes for Docker works great, works on Edge, Mac, and Windows. I heard it works on EE. I don't have a license. And it supports API extensions. It's a certified Kubernetes after all. But what's surprising, you might not know, is that the Docker stack supports actually uses API extensions to implement itself. I think David Gageot talked about it at DockerCon EU last year, but he didn't get into exactly how it works. I'm going to do that. So I'm not brave enough to do a demo, but I did write a script for everything I did that you can go to that URL and try it later and call me on it if it's not real. So I'm just going to do sort of fake screenshots here. So here's a Docker Compose file. A Docker Compose file is like a high-level description of wanting to create pods, deployment services, containers. So I can use the Docker CLI to deploy it, and it says, blah, 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 I'm deploying this thing, Redis is running. And then the whole collection of things is called stack demo. Now, if I want to go look at my Kubernetes cluster and say, okay, what did Docker do to my Kubernetes cluster? When you're using Kubernetes for Docker, by default, when you deploy a stack, it deploys it to the local Kubernetes cluster. So I can check to make sure I'm talking to Docker for desktop. I am. So I can look to see if there's any services. And yep, there's someone called Redis. There's one called Redis random ports. I don't know what that is. Why is this doing this twice? I can also ask it if there's any deployments. Whoops, how do I go back? There we go. Yep, there's a deployment called Redis. So there are objects that are created in the Kubernetes cluster as a result of me creating this Redis stack. So this is a controller pattern Tim talked about. There's a higher level of abstraction that has a high level resource like a compose resource or file. I use those interchangeably. There's a control loop. It looks at the high level thing and it creates low level things. Those are, in this case, it's services and deployments. We see this pattern repeated again and again in Kubernetes. So those resources need a home. Clearly for service and deployment, the home for those resources, the Kubernetes API server, all the deployment resources are a collection of similar type things. They form the deployment API. Same with services. But where does Compose live? Well, you could imagine maybe, like I know how to use Node.js, I know how to use Flask, whatever your favorite language or framework is, I know how to write a REST server. Let me just whip that out. It can have some storage. That's easy. Maybe the Docker guys decide to put it inside Dockerd. They have like a stacks endpoint that you like load it and the controller can look at that. This is hypothetical. It's not how it works. But I did use Docker CLI, so it's not unreasonable to think that's how it works. Let's find out how it works though. Last time we created used Docker stack command to deploy the stack, but now I'm going to run kubectl get stacks. It knows that there's something called a stacks. Did the Docker folks get Tim or me to approve a PR to add stacks to Kubernetes? Tim's shaking his head no. So how's that work? So to debug this, I'm going to put a proxy in between me and the Kubernetes CLI, and I'm going to turn on some debugging. I'm going to split my screen so I can see what's happening on the flow. Now I'm going to get stacks again, and I just added this -s argument to tell it to go through the proxy. So again, I got the stack demo object. It says there's one there. But looking at the output, the verbose output, I see it's actually doing a get on something called a compose.docker.com v1 beta 2 API. How did that get on the Kubernetes API? So what really happened here was there is another API called compose.docker.com that's also part of Kubernetes, and kubectl can talk to it. That still leaves the question, though, of how did that compose.docker.com API get there? So let me drill in some more. This is a magic command that took me a long time to figure out. It's not documented anywhere, so take a picture now. But when I run this command on my vanilla Docker installation, it actually shows 26 different APIs that Kubernetes knows about. And I put a little ellipsis there because I'm not going to show them all. But one of them is called v1beta2.compose.docker.com, which is a bit of a mouthful, but it sounds like what we're looking at. So we're just exploring. This is actually how I figured out how it works. I didn't read the docs or anything. And so I'm going to ask Kubernetes for more information about that particular API, which is one of the 26 groups of APIs that it knows about. And it says, oh, a bunch of stuff, but the interesting thing here is there's a little stanza called spec, service, and it has name and namespace. And it's saying there's a service called Compose API in the Docker namespace. Let me go check that out. I'm listing them, services in the Docker namespace, and lo and behold, there's something called Compose API. And it's backed by a deployment, actually 2 deployments, so we'll have to figure that mystery out in a second. So, we can kind of infer what's actually happening. When you enable Kubernetes for Docker, something in Docker desktop did several steps. I don't really know what order it happened in. Actually, that doesn't matter. That's a good thing about Kubernetes eventual consistency. It started a deployment called Compose API. It registered an API called compose.docker.com. That caused the Kubernetes API server to, out of thin air, create a new Kubernetes API called compose.docker.com. And it caused it to set up a sort of a proxy between that service that backs it and this sort of fake API. And it started a control loop that's going to manage that lifecycle we talked about. So now when some other user comes up with a Docker CLI and then they create a stack, then that actually creates a compose.docker.com resource called Redis. The controller sees it, and then it materializes the services and the deployments. And I don't show it going in the rest of the cluster, but you can imagine what happens. So you might be thinking, okay, why do I know this proxying and this looks complicated? I don't want to do that. Why did Docker want to do this? They did do it. It's because Tim told them to? Let's say that's not why. So here's why I think the good reasons for them to have done this. For users, they already have a client installed. Now they have Docker installed, but if you're someone who doesn't have the sort of mindshare of Docker and you want to create a new API and you want to skip the step where you like create a client and release it and get all your users to install it and build it for like 3 different languages, whatever, we already did that for you, Kubernetes, kubectl. It's there. Lots of people here have that installed. And it already knows how to find your API endpoint, to trust it with TLS, to authenticate your users of your API to the API. For controllers, they can efficiently watch your new resource. And for admins, they know that they can separate resources by namespace. They're already authorizing and audit logging and using RBAC on or whatever you want on your resources. They don't have to do anything. You just install the resource and those things happen. So that's kind of exciting. So this pattern, which I did the specific example with Docker, but it's a more example of a more general pattern where we call API aggregation, meaning you aggregate these subordinate APIs under the Kubernetes API, and these subordinate ones, the one on the left, bottom left, we call that an extension API server. So one of the problems here is these are pretty cool, and people are using them with good success. We've seen dozens of examples of people building on them, Docker, Red Hat, many other people. But you do end up maybe at some point thinking, well, I might need to HA this thing. And I better have persistent storage for my state. It's not such a big deal for Docker because it's on your laptop. But when it's on a cluster, maybe you need to figure out what you're going to do there. And another thing I know I couldn't figure out a drawing for is you have to fork quite a bit of code to make an extension API server that serves exactly the right API to sit behind the proxy. It can't just be a random REST server. Now, one thing you recognize is this is kind of a similar pattern. There's already storage in the Kubernetes API. There's already HA in some versions of it, like if you use GKE. And someone probably, if you're using Kubernetes, whether it's Docker or someone else, you probably have a distribution of it. So someone's managing the release process for you. So why should I do all those things for these bottom left gray things? I agree. We have a different kind of API extension called custom resource definition. It says, don't write a server. Just make the API directly with us. You still need a controller, but it's better. So we have 2 options actually for adding APIs. I'm abbreviating them, extension API servers. People call it API aggregation. This is what Docker currently uses. You're forking several thousand lines of code. You're managing your storage. You've got 3 components. It's got multi-versioning support. It's very customizable. How did this work out? Well, we see order tens of projects on GitHub that are using this. It takes a little bit of experience to get this right. This easier one, called CRD, you don't fork anything. Storage is taken care of. Basically, one component, you need a controller. You might fork some code for the controller. There's no way around that. We see on the order of 400 GitHub projects, distinct, all creating new APIs that you can add to your Kubernetes API. None of them, I'm not counting experiments, some of them are not production ready, but there's a lot of excitement here. And so lowering the bar to adding APIs, we've seen to be really powerful at getting people onto the platform. So, Tim talked about devices, storage, and networking. There's maybe 30, 50 things there. Order of magnitude more things for APIs. So people are much more interested, we're seeing, in customizing the front of the hardware than the plugs in the back. You need both, but this is where the fun is at. Ecosystem, lots of different types of things. Examples, Docker, I showed how others using it. Kubeflow was a popular topic when I talked to people in the hallways. Kubeflow uses CRDs to create resources that are succinctly describe how to create machine learning training or serving flows. Set up Jupyter hubs, things like that. We're seeing in the open source alone, I can't see what maybe startups are doing, but 4 different serverless frameworks, 6 different paths, including OpenShift. You see CI/CD systems, special database controllers. I talked about ML. So, in conclusion, I really liked using Kubernetes for Docker. It was a super easy way to try Kubernetes. I was really happy that it just supported API extensions out of the box. I encourage you to check them out. There's links for more reading there at that link. Maybe even try to author some. Docker's a great place to prototype them. It just works. Use Kubernetes. Thanks very much. We can take questions.
Hello, hello. All right, we're on. If you have any questions, come up to the mic here.
Or just yell.
Or just yell.
We'll hang out afterwards if you're too shy.
If you yell, we'll repeat it.
Are there any plans for CRT versioning?
I think about that every day.
Repeat the question for us.
So the question was, when can I please have CRD versioning? Literally, I talk to people about that multiple times per week. If I have anything to say about it, it will be done soon. You are not the first person to say that's important, and I agree it's critical.
You're probably not the first person today.
It's tricky because it interacts with other things we're doing in complex ways, like we're trying to improve apply. Right now, CRDs don't support apply or last applied state, and so we're trying to move that to the server side. And at face value, it appears that the server side state should probably maybe be versioned, and now you have to convert the server side state. So people are working on that, but I see the light at the end of the tunnel. Yeah. If you use the EAS method, then so the question was, when I use API extensions, does it use etcd? And the answer is, when you use CRDs, you have to use whatever your Kubernetes master is using, which is pretty much generally etcd. There's not a lot of other options there. I've heard people doing crazy stuff, but it's pretty much etcd. If you use extension API servers and you want to keep your fork light, you're going to end up running your own etcd. If you're willing to take a bit of a heavier fork, which is something that, for example, the metrics API does, then you can use what I call a facade pattern, where you use your own storage. And there's no plans to allow alternate, different storage than the Kubernetes master with a CRD path, but it's definitely possible extension API servers. If you want to figure out how to do it, grab me afterwards. I think.
Is there any good documentation to write a fast custom controller?
Talk about fast. So the question was, I guess that was on the mic. Can you say more about fast?
Do you mean performance, or do you mean rapid?
Like a getting started document, or?
I recommend a project called Kubernetes SIGs, github.com/Kubernetes
Kube Builder?
SIGs/KubeBuilder.
Kubernetes.
It automates the whole process for you and it's the best documented of the flows I've seen.
Okay, thank you.
Yep.
Other questions? All right.
All right, thanks very much.
Thank you very